So let's talk about the 2015 questions 4 through 6. And these questions are completed without a calculator. And so in the first question, the prompt tells us that we're going to consider the differential equation. So there's lots of directions that this question can go. In this case, we're going to be looking at the differential equation. And within that differential equation, we're also going to be looking at some implicit differentiation. So you can see the various topics that they can run through with this particular given differential equations. And we're also going to be dealing, in this case, with a slope field and not a solutions curve. So letter A tells us on the axis provided, sketch a slope field for the given differential equation at the 6 points indicated. So what we want to do is we want to take our slope generator, which is what they gave us right here, dy dx, and for every xy value down here in the slope field, we're going to substitute in place of x and in place of y and carefully calculate those slopes. And I say carefully because if you look down here at the scoring guide, we're going to look at the slope field, and here's what it looks like. You get 1 point for having all of the slopes where x equals 0 correct. All of them have to be correct, and if you have one place where the slope is 0 wrong, and I think over here in this given, we only have one place where the slope is 0. And then secondly, slopes where x equal to 1. Oh, I'm sorry, I misread that. It says, yeah, sorry, I was thinking that the slope itself was equal to 0. The slopes where x is equal to 0. So in other words, you had to have all of these slopes right here angled correctly. Now when I say angled, we don't really measure the actual number, but we should see some difference between this negative slope and this negative slope. The slope is steeper at 2 than it is at 1. And then they did not put a point at 0, so we don't need a slope there, and then we need one at negative 1. And then secondly, we have to have all 3 of the slopes at x equal to 1 correct. If you miss once, if it's in the wrong direction, then you're not getting that answer point. So be careful, or that's that point. So be careful with your slope fields because it's just arithmetic. All right, and let me clear the board here. And in part B, we are finding the second derivative. Now remember, when you find the second derivative, we already have dy dx. That was given. When you find the second derivative, the main thing to remember is that every time you take the derivative of a y term, then you have to leave a dy dx behind by the chain rule and the implicit differentiation. And then potentially you will probably, depending on what we're going to have to do, substitute dy dx. But in this case, we might not necessarily have to do that because I don't think that's the end all of the question. Because what they're really asking us to do is after we determine the second derivative, then we want to use the second derivative to determine concavity of the solution curves of the differential equation and pay very close attention. We're focusing on quadrant 2. Now in quadrant 2, slopes are, the x values are negative and the y values are positive. So quadrant 1, 2 is what we're focusing on. 3, 4, just want to make sure you remember what your quadrants are. So when I come down here, look at the solutions guide. Actually, I'll do it for you. Let's go back up here. So when I take the derivative of the left side, I get d squared y over dx squared. And when I take the derivative on the right side, the derivative of 2x is just 2, and that's in terms of x, and the derivative of y is 1 dy dx. There's my implicit, and there's my chain rule. Now, I can, at this point, I can now go back, if I want to, and substitute 2x minus y in place of dy dx, but I don't really have to, because all I'm trying to figure out is what is my sign going to be? Is the second derivative going to be greater than 0 and be original be concave up, or is the second derivative going to be less than 0 and original function be concave down? Now remember, we said we're substituting a negative value in place of x and a positive value in place of y. So let's look at what they did in the scoring guide. So they did what I did. They got 2 minus dy dx. Now they actually substituted dy dx into its place, which makes sense and pretty easy in this case. And so when you simplify and you distribute the negative, this is what you get, although you don't have to distribute the negative. So this point right here, the second derivative, this will get you that first point, just that part right there. Now the reason they're cleaning this up is because now they have to make a decision about concavity. So if we substitute, since x is negative, if we substitute a negative number in place of x, a negative times a negative is going to be a positive. Y is positive in the second quadrant, and 2 is positive, so we're outputting a positive all the time. Therefore, the solution curves in quadrant 2 are all concave up. So you have to be clear in your reasoning and your justification. And then finally, in letter C, I'm going to clear the board again. So in letter C, let me get my pen here. Find the values of the constants m and b for which y equal mx plus b is a solution to the differential equation. So as you can see in my notes, I said, I'm not going to lie, this is kind of hard, and so I'm going to show you different ways to actually do this and try to explain it to you. If you got it, you should be really proud of yourself because, like I said, this is pretty tough. So here's the scoring guide, and you can see, if you're in my class, you can already see that in the solutions, but I'm going to try to explain it to you. So if you look at the second page, the first thing I've done for, or the next page, the first thing I've done for you is that's part B. I showed you student work in part B just to show you what it looks like when a student does their work, but we're focused now on part C. So let's come down here. So we know that the derivative, the slope generator, is 2x minus y. This is the given derivative, it's the given slope generator, it's the differential equation, so it generates slopes for all of the solution curves. Now they're proposing that there is or at least one solution curve that is linear in the form of y equal mx plus b, so it's one of many solutions. This is this particular solution happens to be a line, so I'm gonna start with y equal mx plus b, and I'm going to take the derivative of both sides. So the derivative of y, using the chain rule, is dy dx, and the derivative of mx is just m. Remember, that's already in terms of x, and the derivative of b is 0. So now we know that dy dx is equal to m. So I'm going to take the dy dx that was given. This is my differential equation. They called it dy dx. I know that dy dx is equal to m from my work over here, so I'm going to substitute 2x minus y in place of dy dx and set them equal to each other. So this is where I'm going to start the process. This is not the only way to do the problem, but this is one way to do the problem. So I start here, setting the 2x minus y, the dy dx, equal to m. Now I'm going to combine like terms. So I know from my work, where I'm going to substitute first, I know from my work that the solution curve is mx plus b. Y is equal to mx plus b, so I'm going to substitute mx plus b in place of y. And that's where this came from right here. Then I'm going to distribute the negative and distribute the negative, so that's where the next step comes from. I took the m on the left side and I subtracted it, on the right side, and subtracted it on the left side. All right, now I'm going to gather my like terms, so I see, let me change colors, I see that 2x and mx have an x in common, so I group those together. And b and m are constant, so I grouped those two together and factored out a negative. Now notice that this is a linear format. If I factor out the x, then I get 2 minus m, and this is my constant. So I'm saying, well, if that's equal to 0, that's really the same thing as 0x plus 0 if I'm putting this into an mx plus b format. So then I can take the coefficient of x, which is 2 minus m, and I can set it equal to the coefficient of x over on the right side, which is 0. So that's what I'm doing in the step right here. Then I can set the constant, which is b plus m, or minus b plus m, equal to the constant on the right-hand side, and that's how I got this. I can solve for m to be 2. I can substitute 2 in place of m and get negative 2 for b. So those are the values that I find. So again, I said this is a pretty rough question, and I think it's pretty tough, and if you got it, you should be really impressed with yourself. I did generate the slope field. I took, so let me clear that out and show you what I did. I just wanted you to get a visual. You're not expected to, certainly not expected to do this, but I created the slope field that's generated by dy dx, and that is what you see down here. So dy dx is equal to, I've already forgot what it was. I think it's 2x minus y, yeah. Is equal to 2x minus y. And when I put it into some software that generates slope fields, this is the slope field that was generated right here. I also created the line, or didn't create, but I graphed the line that was created when I get my solution curve. Let's write that out. They didn't ask me to, they just asked me to find m and b. So if y is equal to mx plus b, remember that was one of the solution curve they want us to focus on. M is 2, so that's 2x minus 2. Now right here, over here, that's negative 2, so I kind of highlighted that point. And now I'm going to bring this line, which is the equation of, which is the line 2x minus 2, and bring it over here onto the slope field so that you can see that this actually is, I'm going to slide it over just a little bit. If I slide it off of those slope fields, you can see, like as I slide them closer and closer, it's hitting that particular region where there is a linear solution. So graphically, this is what the work that we just did, this is what it looks like. Again, you wouldn't be expected to produce that, but I kind of wanted you to see what actually is going on graphically. There is another way to handle this problem. The other way to handle this problem is to use your second derivative that you found in part B. So here's the second derivative, which was equal to 2 minus dy dx, and then by substitution, you get 2 minus 2x plus y. Since the solution curve we are considering is a linear solution, y equal mx plus b, the derivative of this line is m. We talked about that in the first method to solve this. But the second derivative, if we go from first derivative to second derivative, the second derivative of m is simply 0. Therefore, we can set the second derivative, which is sitting right here, 2 minus dy dx equal to 0. We know that dy dx is equal to m, so I can substitute that here. And I can quickly find that m is equal to 2. And then I can go back, let me scroll down here. Then I can go back to the first derivative. I remember we know that dy dx is equal to m. And so I can substitute 2 in place of m and substitute 2x minus y into dy dx, get y by itself, and then I can find out that b is negative 2. So no matter how you slice it or dice it, that's a pretty tough part of that problem. However, if we look at the scoring guide, let's see how many points you can earn. So if at anywhere in your work you indicated that the derivative of the linear solution is m. Now I don't know exactly what how they want us to show that, but I guess it's understanding that. And if you set the derivative equal to m, you can get another point. And then if you actually get your answer, you get your third points. So notice you can still get 6 out of 9 points just on A and B. And remember, you don't have to earn a 100 on the AP test to get a 5. You just have to be above average, and my students are definitely above average, so do not worry. Question number 5. The figure above, and it's to the right, shows the graph of f prime, the derivative of a twice differentiable function f. Twice differentiable means that there is a first and a second derivative. It also implies that the first derivative is continuous and the original function is also continuous because differentiability implies continuity. So we may need to know that. Now I'm feeling pretty confident that this problem is a classic all about me sheet problem. And by now, you should be very convinced that College Board thinks this information is really important, so you have to know it. The graph of f prime has horizontal tangents at x equal to -1, so they're just telling me that if I look at this graph, there's a horizontal tangent at -1, and there's a horizontal tangent at 3. The areas of the regions bounded by the x-axis of the graph from -2 to 1 and 1 to 4 are 9 and 12 respectively, meaning in that order. Now notice I did not put a negative or a negative. I did not put the signs here. I'm just saying that this area is 9, this area is 12, and how the direction that I move in will determine whether I count that area as positive or negative, and if I'm using a net or a total. Okay, so that's the prompt, and in part A, we are looking for x coordinates of f original, where f has a relative maximum. We know from the All About Me sheet that wherever f prime changes from positive to negative, we have a relative or a local maximum. And so f prime changes from positive to negative at x equal to -2. There is a critical number at x equal to 1, but there's no sign change, and there is a critical number at 4, but there's also no sign change. So in letter A, we need to tell the reader that the first derivative is equal to 0 at x equal to -2, 1, and 4. Now, notice in the scoring guide, they did not, you don't lose a point if you did not state all the critical numbers exactly. It just says that the student needs to identify x equal to -2. And then your justification is that f prime of x changes from positive to negative at x equal to -2. And this is also an identification of x equal to -2. So this first statement does not necessarily have to be there. All right, going on to letter B. In letter B, on what open intervals from -3 to 4 is the graph of f original, both concave down and decreasing? Now remember, we have the first derivative, so yes, we can talk about concavity with the graph of a first derivative. Make sure you know that f is concave down when the first derivative is decreasing, and f is decreasing when f prime is negative. So be careful, because it's really easy for your brain to mix up the words decreasing and negative and increasing and positive, and they're just not the same. So I'm looking for two things: a place where the graph that I see is decreasing, and a place where the graph that I see is negative. So one way that you could look at that, let me get rid of my stuff up here, is you could start by highlighting the places where the graph you see is decreasing, and the graph we see is decreasing here, and the graph we see is decreasing here. The second thing that they wanted me to, or that I have to identify or consider, is where is the graph that I see negative, and the graph that with the same region. So the graph that I see is negative here and here. So the intervals are from -2 to -1 and 1 to 3, because f prime of x is decreasing and negative on these intervals. 1 point for the correct intervals, and if you put brackets on any part of that, you're going to be okay, and then 1 point for the reason. Okay, let me clear the board here because it's getting a little messy. Let's come back to and look at letter C. Grab a pen. So in letter C, we're finding the x-coordinates of all points of inflection. All About Me sheet. Give a reason. F original has points of inflection where f prime has local max or min, or you could think f prime changes from increase to decrease or decrease to increase. So f prime has a local minimum at -1, a local maximum at 1, and a local minimum at 3. So these are the x values where the points of inflection would occur on f original. The student earns 1 point for identifying all 3 of the points of inflection, and then 1 point for the reasoning. They stated that f prime changes from decrease to increase at those 2 points and increase to decrease at x equal to 1. It's easier, in my view, to say all 3 points because at each of these points, f prime has either a local max or a local min. That would work as well. And then finally, in letter D, in letter D, we are given an initial condition that when x is 1 on the original function, y is 3, we are writing an expression that will generate f original. It has to involve an integral, and then we're going to use that to find 2 y values, x equal to 4, x equal to negative 2. So now we're at our accumulation problem. We have an initial condition. We're going to start with 3 units of area. This is the 3 units of area I'm going to start with, and then all of my accumulations are going to begin at 1. So with 3 units of area, add to that an accumulation that begins at 1, going to whatever value of x that they ask me, f prime of x dx, and this is where my areas that they gave me earlier are going to come in, and the direction is going to make a difference. So for f of 4, we're going to start with 3 units of area, start at 1, stop at 4. That's moving in the positive direction. And since the area in that region is below the x-axis, we will treat it as a negative. Combine and we get negative 9. 1 point for the integrand, meaning that the student indicated that they understand that they're going to have to take the integral of f prime. I don't think you have to have the variable disagreement here to get that point, but it's always nice if you realize that the variable that we want is an x, so these 2 variables should disagree. But I still think you'll get the integrand if you did not change the variable. Also, you can get that integrand point right here. It doesn't have to be a separate statement. You can just start off right here. For f of negative 2, we start with the 3 units of area that are given. We start at our initial x value. We start at negative 2. Now this time, from 1 to negative 2, we're traveling in the opposite direction. So even though that area is below the x-axis, we're going to treat it as a positive. They decided to reverse their bounds here and negate, which is the same thing, and it does not matter. You don't have to reverse the bounds and negate if you understand that you're going to make that area a positive, and you get 12 as your answer. So 1 point for the integrand. Oh, they did ask us for the expression of, I said earlier, and I apologize, that we did not have to have, we absolutely have to have this, because they asked us for an expression for f of x. And I think you probably do have to have the variable disagreement to get that point, and then 1 point for getting both f of 4 and f of negative 2. If you don't get both of them, you're not getting the point. And finally, question number 6. Notice in question number 6, if you just look over here, you might think, oh, here we go again with another differential equation. And it actually is a differential equation. But the focus in this problem, I don't think, in this problem, they're not going to ask us to separate, integrate, solve. We're actually going to deal in this problem with implicit differentiation. So they tell us that we have an implicit relationship. We have some sort of curve that's y cubed minus xy equal to 2, and they are giving us the derivative. So the implicit differentiation for the first derivative has been done for us already. In letter A, we're writing the equation of a tangent line. Yay, that's easy because we just are going to use y minus y1 is equal to m times x minus x1. Dy dx is my slope generator, so I'm going to substitute negative 1 in place of x and 1 in place of y to generate the slope. And I have my x and y values, so this is them here in part A showing the substitution and that the slope is 1. So you get 1 point for generating a slope of 1/4, and then you get 1 point for writing the equation of the tangent line, y equal to 1/4 times x plus 1 plus 1. Yes, you may distribute and combine like terms if you did that correctly. And yes, you may have your answer in this particular case. Why my, let me read that question. Write the equation of the tangent. So yeah, you could, in this case, you got to be careful. And I really don't want you to leave your answer in this format. I want you to always solve for y. In part B, let me clear this out. It's getting messy already. In part B, we are finding the coordinates on the curve where the tangent line to the curve is vertical. So if we have a vertical line, we know that the slope is undefined. We know that if we have a fraction, a numerator over a denominator, if the denominator is equal to 0, the division is undefined. So to find where we have vertical tangents, we're going to set the denominator of our derivative equal to 0. So down here you can see we're setting the denominator equal to 0, and we're going to solve either for x or for y, but hopefully you chose to solve for x because that is easy. So we always want to pick the easy way to solve the equation. Now that doesn't give me the answer, so now this 3y minus 3y squared has to go back up here and be substituted in place of x. And so that's what you'll see next in the scoring guide. So they're substituting 3y squared in place of x. Combine like, or multiply, simplify, evaluate. So we get y cubed minus y squared times y is y cubed minus 3y cubed is equal to negative 2y cubed, and that's going to be equal to 2. Divide both sides by negative 2, and you get y cubed equal to negative 1. Take the cube root of both sides, and you get y equal to negative 1. You can substitute that back into the original. Actually, let's not. Let's substitute that negative 1 back in here and get 3. The tangent line to the curve is vertical at the point 3, negative 1, and they did ask for that. So the student will earn 1 point if they set the denominator equal to 0. They'll get 1 point just for getting the equation in one variable, meaning that they're taking the original, that's this piece right here, the original relation in one variable, and then 1 point for the correct coordinates. And finally, I'm going to clear the board one more time, and we're going to look at letter C. So in letter C, we are looking at the second, we want to evaluate the second derivative at x equal to negative 1, y equal to 1. So remember, back up here, we had the first derivative. We're going to find the second derivative, and we're going to need the quotient rule, down d up minus up d down over down down. Whenever you take the derivative of a y term, you're going to need to leave a dy dx behind. So here we have down d up minus up d down over down down. Now here is my strong recommendation. Do not, in this case, substitute the original dy dx back in here. Do not in this case. Because remember, the only reason that we found this second derivative is to substitute, I think it was negative 1, 1. Let me go back. So we have the x value of negative 1, x value of negative 1, and the y value of 1. So instead of substituting the original dy dx here and the original dy dx here, substitute negative 1, 1 into dy dx, get a numerical value, and bring it down here and substitute. The other thing that I want to urge you with everything within me is substitute these numbers and walk away. Do not try to substitute any further. And I think we had already found, yeah, I'm sorry, I'm thinking, okay. Never mind. Leave your answer unclean, unsimplified. You just don't have to simplify it for the AP test. It is a time saver. It is an error saver. Please don't simplify. you get 2 points for the proper implicit differentiation. So that point would come in the first step. So the first point would be earned by getting all of this correct. So substitution for dy dx, it does not mean that you necessarily have to substitute dy dx into this mess over here. It simply means that you're going to get that's the substitution for the dy dx. We can see that you substituted to get that number, and then 1 point for the answer, which is right here. So take time. If you had trouble with these, go back and redo them. It never hurts to redo a problem, even if you already know how to do it or what's going to happen. You just make sure you get that practice in.